All right. We've been talking about acceleration and force and Newton's laws. And the question I would ask you is this ball accelerating? And the thing to remember about our definitions of motion is that velocity is a speed and direction. So even if this ball is going in a constant motion, if its direction changes, it is accelerating. That means that there has to be a force on it based on Newton's laws. If there's an acceleration, there's a force. So what direction is that force? What's going on to cause this to change its motion? So, and what happens when that force lets go? It goes off in a straight line because it has inertia. And that inertia continues it in a straight line. And so I want to talk about the force that causes circular motion today. And that force that causes circular motion is the force that is aimed towards the center of the circle and gives us the change in velocity, but not the change in speed necessarily, but the change in direction. So an object moving in a circle has a force acting on it. That force is aimed towards the center of the circle. Now, this is a circle, this is a turn, so it doesn't have to be a full circle. Anytime the direction is changing, there's a force acting on the object. So we see here, this is just showing us that the velocity at instant 1 is different than the velocity at instant 2. Even though the vectors are the same length, they're in a different direction. So that means they've changed their velocity, so they've accelerated. And the direction of the force is aimed towards the center of the circle. This is called a centripetal force. Centripetal means towards the center. And circular motion is caused by a force moving towards the center. And we use this formula, mv squared over r, to find how much force that is. So it depends on the mass. If I have more mass, it takes more force to turn it. No big mystery to us. We know that when something has a lot of mass, it takes a lot of force to turn it. And we can see that when we're trying to change the direction of something that's large, whether it's a vehicle, whether it's an object that's moving, it takes force to turn it, and that force needs to be perpendicular to the motion. So centripetal force is always a force that maintains its perpendicular orientation to the motion itself. It doesn't slow it down or speed it up. It causes it to change direction. And our formula is mv squared over r. This is centripetal force. Now, some people talk about centrifugal force. Centrifugal means away from the center of the circle, and there's really no such thing. Centrifugal force is a force that we've made up to explain what we feel when we are forced to go in a circle. If I'm going in a car, let's say I have something hanging off my rear view mirror. This is an accelerometer. It's perfect for an accelerometer. If I accelerate forward, it moves back. If I slam on the brakes, it moves forward. Think of it this way. If I go in a clover leaf, which is to my right, that's going to go out like that. In other words, this always tilts in the direction away from acceleration. If I accelerate forward, it tilts back. Accelerate backward by hitting the brakes, it tilts forward. If I turn that way, it tilts this way. That means the acceleration is in that direction. All right. That means the force is in that direction. There's no force pushing me to the outside of a curve. My mass has inertia, and my inertia continues me going in a straight line. But when I am forced to go around a curve, the side of the car pushes against me. So what I'm feeling is the reaction force from my shoulder to the side of the car compared to the action force of the side of the car against my shoulder. If the door was open, if I didn't have any friction between myself and the seat, I would still go straight forward. But the car forces me around the circle. That's what centrifugal force is, and there's no such force. That's not a force that's causing me to go towards the outside. It's my inertia. So centrifugal force is a mythical force, and it's used way too often. what we're seeing is centripetal force. So we need to know the mass and the velocity, and that velocity is in a circle, and the radius of the circle. Now, that means that centripetal acceleration is v squared over r. So if you want to know how rapidly something's accelerating, you just take the v, the velocity of that, and it's a linear velocity, how fast it's moving around in the circle, squared divided by the radius. The tighter the turn, the faster the acceleration, because the radius is smaller, so that increases the acceleration and the force. Now, this is a great formula for us, except for the fact that sometimes we have lab situations where we don't know what the velocity is. So we have to measure something else. So we have to measure the period, the time it takes to go around one revolution. So anything that has a regular cycle that happens at a regular rate, we call one happenstance the period, the time that it takes to happen once. So we take the circumference of the motion, 2 pi r, and divide it by the period t. So whenever you see capital T, that means period. Lowercase t just means elapsed time. So we can then substitute that into the mv squared over r, and we end up squaring it, and the radius cancels out the radius on the bottom of the centripetal force formula, and we get a new centripetal force formula. This is the one that we can use in labs and things like that, which you'll use in the lab to come on centripetal motion when I wheel around a rubber stopper, and you'll have to solve for forces and masses and different things like that. So this is a handy formula to use. It's the exact same formula. It just happens to use radius and period instead of velocity and radius. All right. So when we have something that goes around in a circle, it could be a tension like I had with the ball, the tension of that guy pulling. He's got to continue to pull that ball in. If he does not continue to pull that ball in, the ball moves off in a straight line. Now, if there was a centrifugal force, that ball would move off in a line parallel to the actual rope. So when the rope breaks, it's going to go in the direction of the break of the rope. But we know that if we have that situation, that ball is going to go tangent to the circle instead of straight out. It's just like if I was wheeling around a bucket of water and the bucket broke, the bottom of the bucket broke right here, the people that were in front of me would not get wet. The people over here would get wet because the water then continues in a straight line. So generally what we're doing when we're talking about circular motion, we're talking about a consistent force. So usually when we talk about something that we're wheeling around, we're talking about it horizontally, because if we do it vertically, now we're increasing the force when it's down because of gravity. And so I've got to give both the force to keep it moving in a circle and the lifting the weight, versus here, and it doesn't feel as much force. So I can feel that there's a difference in the amount of force if I do this vertically versus if I do this horizontally. Horizontally, I feel the same amount of force the whole time. And that reason is because it's moving perpendicular to gravity, and gravity does not affect it differently based on its position. Here, gravity affects it differently based on its position. It affects it well, not differently, it affects it the same, but because its position is vertical, it's not going to feel the same because I have to put different amount of force. It varies the amount of force. If we look at this car, the friction of the car's tires on the road are causing it to turn. So the friction has to act perpendicular to the direction of the car's motion. So when we have a situation like this, if we don't have enough friction, the car is going to keep going straight. We have snowstorms coming up soon. We have ice on the roads. And if our car's tires don't have friction with the road and we try to take a turn, we're going to go straight. So that's an important aspect to understand. There has to be something that provides that centripetal force to cause us to turn, and that force acts towards the center of the curve. That's why we have banked tracks and roads, because that reduces the amount of friction necessary when you're taking a turn. So keep in mind, if we are looking at this car on a banked road, the normal and the weight are not the same. The normal is less than the weight. So we can take a turn at a faster speed without skidding out. And so the faster the road is made for, the more the bank. So when you see racetracks, they really bank them an extreme amount because those cars are going in the 200 mile per hour range. This car on the bottom here is going straight, but it's on a road that has a dip in it. And so at the bottom of the dip, there's more force because that road is now going to push that car up to cause it to change direction. Not change direction in terms of the steering wheel, but change direction in terms of the vertical motion. So the normal force has to increase based on the velocity, because that's a centripetal force type thing too. All right. So if you're in the car in a situation like this, you're going to feel like it's like you're heavier and like the car is heavier because it's being forced up in a curve, and the force upward in a curve from the road is going to be greater than the weight of the car and your weight. So if you were have a scale, you would weigh more. It's the same concept that we have in roller coasters and things like that, like the Wild Thing. All right. So I wanted to talk about that circular motion. We'll have some examples of that in the problems from the book. We'll have a lab with that in the next couple days. Okay. Now, if the object is also increasing its speed, that means it's got an acceleration towards the center, the ACP, that's centripetal, and the acceleration along the tangent, AT. That means that more force has to be acting on it than just the force to keep it moving in a circle. It's speeding it up in this particular case. So that means the direction of force at that instant is a combination of those two vectors. We don't worry about that too much, but if you're trying to speed something up or slow something down, you know you're putting more force or less force respectively on it. And that's what causes it to change. And the direction of force is a combination of the direction directly into the center and along the tangent. So we have a little bit of a difference there. And we would just do a vector diagram to figure that out. I don't think I have you doing any problems like that, but just so you know, that's a possibility in terms of understanding what the vectors have to do. All right. So this chapter has been mostly friction and connected objects and circular motion. So that kind of summarizes what the chapter is. So start working on the chapter problems, and those are going to be due later this week. And keep up the good work, and I hope to see you soon. Thanks a lot.